Hello.
Yes, sir. Started, sir.
Yeah. Okay. Yeah, I have. So let others join. Is it? So how many people have confirmed joining for this session?
We'll check, sir. We'll check, sir.
If they want, I can share screen also, but I don't know who.
Yes, sir.
Yeah.
No, share your screen, sir.
I'll share my screen. Okay. Good.
Yes, sir. Yes.
Yeah. So that if anyone is asking any question or something, I have my pen and thing ready. Yeah. But do you know what's the number who would like to join?
Sir, send the announcement to all, sir. I don't know exactly, sir.
Because some people told that they have forum thing and all, so they might join. But when will they join? I don't know. Vivek, you are there, right?
Yes, sir. I'm here.
Oh, so this invite has gone to all students, is it?
Good morning, sir.
Yeah.
Yeah, I'm Ravikant.
Yeah.
Sir, this is regarding the model we have used for the ordered structures.
Yes. Yes. Okay.
So, how will you accommodate the presence of vacancies, sir? Because the sites are either occupied by A or B.
So this is not a compound energy formalism. It's a very good question. It is not a compound energy formalism where I can actually look at vacancies or electrons. But here it is a much simpler model based on regular solution where we do not consider vacancies. However, if you want to consider vacancies, this is always possible. You can basically have like A, B, or C, D. Think of two sublattices where one sublattice is occupied. So I'll just take a page. 1 second. I'll just take a page to explain to you. It will be easier. Say, think of this way. You have, say, something like you have here lattice. Just okay. So you have some sort of a lattice here. Okay, so excuse my diagram because I'm trying to do it fast. So now you think of this. What your question is that if I have vacancies, how do I accommodate that in my lattice? Correct. So basically, if I have a lattice model, then how do I do that? So now I'll just tell you the way I'll do it. Means the way you will think of doing it is this. You have, say, A side, say this is your A side, and this is another A side. All the face centers are your A sides. Okay. All the face centers are your A sides. Yes. And your B sides are, say, for all the corners. Okay. Now the sides are now specified. Okay, so all the corners. So basically, B are corners. So let us call it, instead of calling it AB, because then you will get a bit confused. Let's call it alpha and beta. Okay, or whatever you feel like. Means you just give 2 types of sides or 4 types of sides. It can be even, see, in BCC-B2, we looked at 2 sublattice model, but you can also go extend it to 4 sublattice model, right? So, okay. So you can do anything. However, say if you have 2 sublattice model, say let's call this, these are your special sites. And these are your another set of special sites. And let's call the tick mark something. Say instead of calling it A and B, I am calling it small a and small b, so that you do not get confused. So small a is basically, say for example, your this blue crosses, and small b is and small b is basically your the green ticks. Okay. So now within A, okay, so now within A, what I am trying to say is that I have 2 types of matters. Okay, so I have, say, A as well as B. Okay, and within B, I have now 2 types of atoms, C and D. Now think of replacing B by vacancy.
Okay.
You got it. So now if you have that, now you exactly approach the same way. You understand? However, right, you have to be very careful. You have to be very careful when you look at vacancy interactions. Okay, we write a regular solution model. So there, how do you generally like? Say, for example, if I have just a binary model which has pure A and vacancies. Okay. Now, if I tell pure A is so we are basically thinking of vacancies as substitutional elements, isn't it? So basically, right, the atoms are there, and then where atoms are missing, we call it a vacancy. Now, if you have that, so if I have my mole fraction of atoms is, say, or I can tell this is XA and this is XV, right? So basically, this is a mole fraction of XV. Now you see, you have omega XA XV. Now this is like a vacancy association energy, It's like a vacancy association energy. Means it is possible that it can be positive, it can be negative. It depends on how much, or vacancy binding energy, like of these atoms, okay, of A and B. However, there is one problem when it comes to ABV. Say I have now a model where I have A and I have B and I have VA. Then I have how many interactions? A interactions are possible, B interactions are possible, AB interactions are possible, A vacancy interactions are possible, B vacancy interactions are possible. Now comes this very strange interaction, which is called vacancy interaction.
Vacancy. Okay.
So in general, for the vacancy interaction, we generally can take it as 0. Okay, the interaction parameter. So for example, if I use a regular solution model, I will have like omega AB, for example, which is basically to say, for example, I'm just giving an example, 2AB minus EA plus EBB. So, and then you have, say, omega AB is there. Now AVA. Now this will be basically 2EAVA minus EAA plus EVAVA, right? Many a times this EVAVA is nothing but 0. You get the point?
Right.
So this term will be there. So this term will be there. So as you can see, this will be there. This will be there. This we can take as 0. Okay, unless you have really some frequency interaction or something. Okay, so there are many. So basically, if you want to go deep into CalFAT, by the way, if you really want to go deep into CalFAT, I can basically give some extra pointer to that. But however, it is not like it was not the intention to go into as many quasi-chemical models as possible. So otherwise, if you go deep into CalFAT, then because CalFAT by itself is a new is one course, you get the point. So there is something called compound. So if you remember, or if you have seen that, there is something called compound energy formalism. Okay, that is what was proposed by Hillard. But if you want some notes, I can definitely give you. Okay, and some explanation. But this in this formalism. But please note that whatever I have told, it is just it. See that once I have told us sublattices and side fraction, that same thing's coming. Only thing is now it becomes slightly more complex because each sublattice can now be occupied by several different species as well as vacancies. Okay, vacancies, as you know, are equilibrium defects. By the way, this is something I did not have time to go into because because it's a bit of intense syllabus. I know that I proposed, but I also wanted to make it as easy as possible. So that fundamentally you understand all the stuff, right? The equilibrium stuff. So that's why I did not spend too much time on the models. But if you want, I can basically give some additional explanation on this compound energy formalism, which is the formalism in general followed. You have heard of this Dirichlet-Fisher polynomials and all this stuff, right? What is basically fundamentally followed is called this compound energy formalism. Okay. So to model these things, but however, if you follow the way that I have done it, actually I have given reference also Swalin's book, right? Swalin basically first showed that, and if you follow the example that I have given, okay, only thing I have derived all the Swalin's book. What happens is sometimes Swalin and all they skip steps. I did not skip any step. If you see that, so I don't want to. So if you follow exactly the steps and just put A, B, and C, D, you should be able to derive it on your own. Okay, and if you can derive on your own, share with me. If there is some problem, I can tell you what is the problem.
Sure, sir. Thank you so much. Sir, actually, there is an extension of this question also. I don't know if you can spend some time on this.
Okay, yeah, please continue.
I am a little exposed to thermocalc also.
Oh, very nice. Okay.
So I am actually from Baba Atomic Research Center, sir. So I have taken this as a part of my PhD coursework, actually.
Okay, so I'll do one thing. This thermocalc tutorial thing, now I will post it separately. Okay, although there will be no questions in the final about thermocalc, but I will do that with the academic version. And by next week, I will basically create a tutorial with thermocalc. Okay, so that you can do the basic kind stuff. For example, free energy composition diagrams, determination of single point equilibrium, and all this stuff. mostly using, the command line and stuff. Okay, so that you can get most of the important properties. Yeah.
Actually, I have used it. My point of, asking you this question is, like, you have an option of calculating the driving force for the phase formation in thermocalculus.
Yes, phase transformations. Yes.
There are two ways of doing it. One, you suspend the phase and get the driving force, right?
Yes.
And second is you keep all the phases selected,
right,
and then just plot the driving force. Whichever doesn't have a positive driving force will appear below the that line passing to the origin, and whichever has a positive driving force will all be at zero because the phase fraction is adjusted to make it zero.
Right.
So now the question is, suppose if I want to find out, like I have a system, I have a case where there are two competing phases.
Okay.
One is metastable phase, and the other is stable phase.
So okay, say let us start writing the problem. So you say, for example, alpha is your stable phase and beta is your metastable phase. Okay.
Right, sir. So both are actually precipitating for the matrix. Let us assume that both are precipitate phases.
Okay. So gamma is your matrix phase. Okay.
Right, sir. Right. So if I actually look at the equilibrium sequence or the precipitation sequence in this, it could be like alpha would come first, and then it will dissolve and give rise to beta, because beta comes first and beta dissolves and gives rise to alpha being the stable phase.
Okay.
Maybe
it
like
is dissolving. You are sure that it is dissolving?
Yes, sir. Like I'll take the specific example. Like it is cementite and Cr23C6. Like in chromium carbon steels.
Okay.
If you have like five chromium or 2 chromium steels, you have like Cr23C6 being the stable phase.
Right.
But when you're quenching and tempering it, the first phase to come out is cementite.
So see, you have already given the answer. Yeah, continue. Yes.
So now the question is, there is one more problem in my case. There is a Cr7C3 phase also, which can come ahead of Cr23C6.
Okay.
Now what happens? There is a competition between Cr7C3 and Cr23C6. So sometimes what happens is prolonged aging doesn't also take me to Cr23C6. So what I believe is Cr23C6 and Cr7C3 might be having a driving force which is very, very less.
Absolutely.
So now
there is one point.
Yes,
Are you basically, is it that Cr23C6 has to decompose to Cr7C3 or whichever phase you are telling, or is it that it dissolves and another phase forms? Have you looked at that?
Yeah, usually what people say is that cementite to Cr7C3, it is more or less in situ transformation. That Cr7C3 forms by a rearrangement of the atoms within the Fe3C cell.
Okay.
So that's an in situ transformation. Whereas the other part, Cr7C3 to Cr23C6 is more like dissolution and reprecipitation.
Okay. So now you calculate two driving forces. Say, for example, let me just tell you, if you suspend Cr23C6 and calculate the driving force for Cr7C3 with your what you have, ferrite and cementite, right, in your solution?
Right, sir.
Yeah. So that is your initial state, and your final state is some phase called Cr7C3. What is the driving force? Have you calculated?
Yes, sir. Yes. So now what happens is I have done it two ways. Like I said, I actually make both of them suspended.
Okay.
Fraction fixed to zero.
Okay.
So, and then I have just plotted what is the driving force with respect to temperature in this alloy for Cr7C3 and Cr23C6.
Right.
So wherever there is a higher driving force for Cr7C3, that is the temperature at which that is more stable. That is how I understood.
Obviously, if it has higher driving force, the higher driving force basically means Cr7C3 will form more readily than Cr23C6.
Correct, sir. Yes. So the question is, there is a contradiction to this. I mean, I don't have the data right now to show you. That's very unfortunate of me. Otherwise, I would have definitely shared the data with you, because that is in my office, sir. I didn't get it to my home. I am talking from my home. Okay. But my phone is not allowed in my office.
Okay.
So the thing is, we are trying to explain some of the carbide precipitation sequences, sir. So now if I do this, so what happens is Cr7C3 shows a higher driving force, but in actuality it is a metastable phase.
Oh, okay. Okay. So do you have the free energy? Say, for example, you know the compositions. Why
Yes,
don't
sir.
you see in thermocal, there is a way to plot all these free energies, okay, as a function of composition. You
Right,
can
sir.
draw like a quasi-binary way. You don't have to basically do a ternary
Okay.
surface, but you can
Okay.
do like along certain, carbon composition or certain, means you fix one of the axes, like
Right.
FeCRC is there. So you
Right.
fix, say, for example, the some ratio between CR and C, and you can do multiple such lines. Okay. So
Correct.
do you have that free energies? Then you will understand the crossovers. If you remember, I gave
Mm-hmm.
one example where I had basically thought of this epsilon phase formation and this beta phase formation. So I have actually worked it out also. It is in the titanium alloy. If you
Right, sir.
remember, there was in titanium alloy, there is a competition between this metastable and stable phase. And in
Hmm.
certain conditions, the metastable phase becomes stable. And in certain conditions, that it directly goes to the stable phase. So
Okay.
basically, it was, I think, yeah, it was basically, it was not as complex as your problem, but the problem was very simple. My problem was a little bit simpler. We made it simpler. The
Hmm.
epsilon phase is the HCP phase, which happens at room temperature. Then
Right,
at
sir.
higher temperature, it becomes beta, and then it beta melts. But we told, say, beta does not form. What is the melting point of epsilon? But the way we did this, if you have to look at the delta G's, there is one very interesting thing you will see, that when I go from epsilon to L, it is basically, you can see that it becomes some summation of epsilon to beta and beta to L.
Yes, yes, sir. Right.
Right? So it can be written. So exactly this is how you can solve this problem. Okay, but so the only information that you require is the free energy curves of each of these phases.
Oh,
I don't think, see, there are two ways of doing it. Suspending is one way. There is also, you can keep them dormant, and you can basically allow them to be calculated in the equilibrium. And
yeah,
then
right.
basically, yeah, and then you can draw one phase free. This basically, I want the DGs. Okay,
Right.
so
Right.
DG is what I require for each of these phases. If you can show me that, I can show you that what is the problem. That the problem is that certain compositions are the way it is forming. You are basically seeing this opposite trend, and in certain compositions or certain conditions. See, ultimately, as you have seen in my lecture throughout, that all your temperature. See, ultimately, see, if you are looking at I'll just do it with a binary phase diagram only. So let us say, if you are looking at a phase diagram like this, and say, for example, you have this type of a curve. I have not drawn the full one. So basically, I have now here it is alpha plus beta, and here it is, say, alpha, and here it is beta. However, what you are telling is that now instead of beta, there is like a beta 1 that is also possible, right? That is, sometimes it goes to beta 1, sometimes it goes to beta. Now, what we have to understand is, where does the see when I draw the free energy composition at a given temperature. So this is always free energy composition is drawn at a given temperature. So at
Correct.
the temperature of transformation and just below the temperature of transformation, if you basically look at that, then you will see the free energy composition curves are like this. So at the temperature of transformation, you will see basically all the curves coexist. You can basically draw some sort of, means basically you can draw a tangent line for all these phases. You get the point. It's like all the phases can coexist at some, but just go below that, and that is where you are seeing. So what I am trying to say is there a defined metastable to stable condition in your system? Because I
No.
don't know your system, but
No.
if you can just, if you can show me that data, I can basically give you the answer. That
Okay.
is for
Okay.
sure. Because I
Definitely.
require to know see, there is something called T critical. T
Hmm.
critical is where you
Hmm.
can have all these energies being almost similar, or
Right.
not energies being similar. You can draw a common tangent to this. Is that type of a possibility there, or is it that always the things are like one is below the other?
Okay. Okay. That part I have to check.
That part, if you check, because see, what you are trying to say is that in some cases, even though CR7 C3 is even though CR23 C6 is stable and CR7C3 is metastable, you get CR7C3 or CR23C3. Which one?
CR7C3, sir. CR7C3.
Yeah, you are always, so basically you are always getting the metastable one. So basically, although the driving force for the stable phase is more. That's what are you telling or not?
Right, sir. Right.
Exactly. So now we have to see the steps, because now think of this. Okay, now let me give you another example. Now let us think of this. Okay, this is an interesting example. Yeah. So if you see, say for 1 second, I cannot draw this. I'll draw by hand only. So if I have a free energy curve like this, okay, now I am here. Okay, where do I go?
Yeah, correct. Depends on
what? Depends on what?
Depends on which way you're perturbed, or I don't know. I mean,
both are possible.
Yeah, both are
will
possible.
I fall here or will I go there? Because I am in a very unstable state. Unstable state has the highest energy. Now I can go to both, and you see there is both are likely. So as a result, it is very important to look at the slopes. And so that's what there is a quantitative way of doing this. You have to look at the slopes, the del G del X thing, and you have to see, because the slope is basically the chemical potential difference. See, the point is, this is a very important point. I don't know, I must have told it, but anyway, yeah, I have told it. So I told it, but anyway, I'll just show you. See, this is a point. Let's see, ultimately, when you draw a tangent line to this, okay, you draw a tangent line to this. See that these are your intercepts, right? So it's like you have, say, A and here B, and these are your intercepts, like mu A, say this is alpha, and this is, say, mu A beta. But what about mu A beta minus mu A alpha? That is your chemical potential difference. That is what determines. So exactly, are you seeing that? So you find that instead of finding the intercept, sometimes we have to find the slopes. Many times the diffusion potential or the change is driven by the slope, not by the exact, not by the values. Yeah, it's not the values that are important, but it's the slope that is important. How is your energy landscape sloping? Okay, so if it slopes one way or the other, you can go. So if the slope is stiffer in one, that is where the transition will go. It is not the relative positions of the minima, but it is the slope that matters. From the position that you have started, from the composition that you have started on the free energy curve at that temperature, find the slopes for both and see which is the slope that is the steeper one, and the slope basically is nothing but the chemical potential difference, right? Because you have these two intercepts. So basically, what is your, say this is G or GM, let's call it GM. So this is your GM curve. So del GM, and this is, say, X, and del GM del X is nothing but mu A beta minus mu, or mu B beta minus mu B alpha, correct? By 1. So this is exactly what I want to see. This is where all the transitions will basically, if you see, just by looking at, this is something I don't know whether I gave example. I think I gave, at least in the phase separation case, I gave example. You have to basically look at the slope. Okay, otherwise it becomes very, very difficult. You can see the problem here, the puzzle here, because you don't know whether the ball will move this side or it will move this side. But if you now know the slope, you can basically tell.
Sir, if you give me a option,
yeah,
I can just share a screen with you.
So this is something that only our organizers can help.
Oh, okay, sir. Okay. I don't know how to, or else I can do one more thing.
Because but there are other people waiting. Yeah, see, if others have also questions, please start asking.
Yeah. Okay. So, okay. Thank you.
So, but what you can do is you can send me an email, okay, or post it in the forum, and then I will definitely answer.
Yes, sir.
Okay, or you can send me an email also. I have already told that you please send me an email where you have doubt. I can definitely try to help you. Okay, Mr. Ravikant, so I can basically definitely help you. Just send me an email or something, because right now I don't know how to share, because this is not organized by me. It is organized by the NPTEL team. I don't know whether they will allow you to share the screen. Is there any other question, Mr. Kaushik? Means any question other than that?
Good morning, sir.
Yeah, morning.
Sir, this is regarding that exam part.
Okay.
So we'll be having exam in this end of this month.
Yes.
Yes, sir. So what we can expect in the paper, sir? It's like what should, hey, question I'm not asking, sir. I'm asking pattern of the paper.
Yeah, so I'll tell you. The pattern is basically very similar to the pattern is very similar to the assignments that I have given. However, I have made it slightly more subjective, so that even if you do not give the correct choice, but your steps are correct, I want to award marks. See, what happened in assignments is that it's very digital. Okay, so basically you give up option. Sometimes even if your option is slightly here and there, okay, but you have actually given correct, you know the correct logic. Sometimes what happens is you get some small problem. But here I have, that's why in the finals, based on the lecture notes and the assignments, if you can go through them well, and you can basically reason with the answers. Okay, so apart from giving the correct option, there is a chance to basically rationalize your answer. Okay, so sometimes even if you do not give correct option, see, if you give correct option, anyway that will be taken. But if you do not give correct option, I want to see the rationale behind choosing the other option, because sometimes the rationale is given correctly, but because of some miscalculation or other, you have given a wrong answer. Understood? So that is why it is subjective. Okay, that is, and also there are questions where you can just draw some free energy composition diagrams that I have drawn, or from the free energy composition diagrams you can derive phase diagram, or you can look at a phase diagram and identify what is wrong with it. Okay, so this type of question.
So logical reasoning based on what you have taught in the class.
Exactly, everything based on what I have taught in the class.
Yes, sir.
Say, for example, I'll tell you, if you have an inclined tie line, for example, in a phase diagram, you definitely know that is wrong, correct? Say, I draw a phase diagram. So I'll just give you an example. Yeah, I don't want to give away everything. You get the point. So, oops. But say, for example, you have some phase diagram. Okay, so let me draw slightly more precisely. You have some phase diagram. And I'll ask you guys, what do you think? What is wrong in this? And okay, so now you have also this one second. Yeah. So this part is good enough for me. Okay, so I don't want to draw the full entire thing, but if you want to draw, you can. So I have this. Okay, so 1 second. And okay, so instead of drawing this line, I draw this type of a line and tell you what is wrong in this diagram. Can you not tell?
Yes, sir.
So this type of questions will be there. Okay, so this type of questions are also there. So basically, so you basically, what do you apply? What principles do you apply if you want to say, or is this sudden change possible? Unless there is one, so you are looking at binary phase diagram. If you want to say that what is wrong, what generally you invoke? Can you tell me? Gibbs phase rule, right? So basically you look at whether Gibbs phase rule is violated or not, right? So this is something that you basically you know how to derive, right? I have derived it, right, for you guys. And also I have told you that basically is a consequence of the phase equilibrium things like T alpha equals to T beta equals to some T gamma equals to dot dot dot, and then P alpha equals to P beta equals to P gamma, then dot dot dot. And then you have like mu A alpha equals to mu A beta. So basically, whenever I give you a binary phase diagram like that, you try to apply your Gibbs phase rule and see whether everything makes sense. You understand? Where it does not make sense, you immediately know what is the problem, isn't it? See, that is one thing. Second thing is, apart from Gibbs phase rule, you have to look at yeah. So that is basically it. But for example, in Gibbs phase rule, I'll just give you one small trick question. So if I just ask you this, say I have a liquid phase, I have a solid phase, but in my phase diagram, I also have gaseous phase. And then you are implying, so F equals to C minus P plus 1. Is that correct? I have liquid phase, gas. So I have a binary phase diagram, which has liquid, gas, and solid. Now I have gas phase. Remember, can I use this phase rule?
+2.
Exactly. You should use +2. In that case, you cannot use this. So you have to use +2, C minus V +2, because you have a gaseous phase, right? So these are small stuff. In fact, I have also told you, if you have all condensed phases, F equal to C minus V plus 1 is fine, because you are assuming pressure to be fixed. See, whenever I fix stuff, you can basically remove it, right? So you basically remove it only when the pressure can be fixed, right? Otherwise, you cannot. But you cannot fix pressure when you have a gas phase, because you have a PV work which is substantial. So as a result, there'll be a volume exchange and all this stuff, volume redistribution. So basically, you cannot really ignore P alpha equals to P beta equals to P gamma, right? In some cases you can, but you have to show that yes, indeed, even if solid, liquid, gases are coexisting, it does not really matter. You can still apply C minus P plus 1, but you have to show that. Otherwise, it is C minus P plus 2. So these type of small, these are like, if you just think a little bit based on what I have taught, you should be able to answer everything.
Okay, sir. Sir, can we expect some derivations?
Very simple, like lever rule type. Yeah.
Okay, sir.
Not much. Or Gibbs phase rule type.
Okay, sir.
Hey, I can't give away everything.
No, sir. Just a broad idea.
Derivations are something like where I give options.
Okay, sir.
Okay, but I tell you, see, the problem is this. Exactly, Kaushik, the point is this. We ask for derivations even though there are options. So why am I asked here is because of the following reason. Sometimes people try to derive in a hurry and write one option. The option comes slightly wrong. Okay, but wrong because you have chosen, say, a wrong expression. However, if you would have derived also, you would have actually given the correct expression first thing. Otherwise, even if you have chosen a wrong expression, you have given, say, the small derivation which points to the correct expression. In that case, I will basically take your correct expression that you have derived. You understand? I will ignore this option thing because that is why I have made it a slightly subjective. Because in the finals, otherwise, it becomes very bad that the computer basically will just look at your option and give you 0 marks. But that is not really true because you might have made a very silly mistake, or you might have just carelessly put that option, but you have derived something else. You get the point? And I'll tell you another thing. In fact, one of the students complained. See, they used some students. So when I generally do this delta G and all for reaction or phase condition, what I do, if you remember, my convention is also always delta G is GF minus GI, right? I take final minus initial, right? Final state minus initial state. But if I tell delta G, say for example, if I tell delta, say for example, delta H alpha to beta, I will basically write it as H beta minus HR. Okay, so one student, okay, one or two students did the opposite. Okay, alpha to beta is alpha minus beta. Now what happens is I have followed that convention. I have given option. but some students just got the negative of it. Are you getting my point? Now they have typed that, and that came wrong. Okay, now you see, if I would have, so I have already basically raised this issue, but this is why the final exam, which is like a 100-mark exam, I have taken no risk, and I have basically, I want to see the answers. Okay, even though there are options, okay, there will be some options. Somewhere you have to write like 1 line, 2 lines. However, it's not a lengthy paper. Means you don't have, you should not write like 10 paragraphs. Okay, only 3-4 lines are maximum required. Even derivation, just very simple 3-4 lines of derivation is good enough.
Okay, sir.
Yeah.
Sir, not connected with this course, but will you be taking some other course in next semester?
I'll see. I'll definitely see. I'll let you know. I'll let you know. Yeah. Yeah. So because the lot of these things, we have to take some time to prepare it so that you understand most of the stuff. Okay. And again, you have some 2 weeks gap. If you have any question, please ask us. Okay, regarding the assignment or anywhere you have doubt, you please ask us. Myself and my TA Vivek, we will try to answer you. Okay. So that is something that I am telling you guys, that please take this time to just ask us any doubt that you have in the concepts. Okay. So the way we have tried is that, see, many a times in textbooks and all, what happens is there is a disconnect from one chapter to the other. So you read Raoult's law, but you don't know how to apply it when it comes to phase boundaries. But we have basically shown examples where we have tried to connect the previous lesson with the next one. So you will see, if you hear the lectures, I think we have tried to make that as continuous as possible, where there is connection between from one to the other. I hope that you have seen that.
Yes, sir. Yes,
I don't know. Yeah. Okay. So this is what I want to do. So that's why, if you see still, there may be, see, I am telling you, we can, as teachers, we can always improve. Okay, there is no best teaching. Okay, so there is always, like, we have so much scope for improvement, right? So this is again also another thing, that this is the first time, so I could not give you all the solutions, that I could not prepare all the solutions immediately. I have all the solutions, but I could not prepare separate lectures for the solution. That is why take an opportunity to collect whatever you are not understanding. If you can send me the mails, I can think of a separate lecture where I discuss some of these solutions where you have doubts, and in that lecture I will provide those some details about that, how to carry out that. So please go through the assignments once again, and the lecture notes that I have posted up to 10th week is now posted. Okay, and look at the lectures. Okay, so that is something that I have also in the last lecture. If I don't know whether you have heard it, that, so one thing I'll tell you, the interfacial thermodynamics is something that I'll not ask, because I could not find any time to do it in detail. Okay, and also the irreversible thermodynamics, where I connect kinetics and thermodynamics, right? Where I look at the Onsager's reciprocity relations and all. I have done that, but I do not want to ask any questions from there. Okay, so those two parts you can basically ignore. In fact, if you look at the lecture, I announce it there itself, that I am not going to basically ask any questions from there. Yeah.
Thank you, sir. Thank you. Thanks a lot.
Yeah. Okay. Akshayji, is this recorded? Then it would be nice. Now we could have. I don't know whether the thermodynamics goes. The organizers are there. Vivek, is this recorded?
I don't think so, because here the record button is off. I think they are not recording it.
That is bad, because whatever discussion we had, we can actually post it there. So
Yes.
anyway, but whatever doubts you guys have, please ask. Don't hesitate to ask. Just ask questions, and we will we'll try to answer. When is the exam, by the way?
It's on 28th, sir.
So there are there are at least, so there is at least 1 week, right? So basically this week it is Friday, but if you can ask by Sunday or so, okay, or by Monday at least, so that I can basically take another like tutorial lecture. Okay, it's like a recording only, but I can post that lecture and I can ask the NPTEL team to post that lecture, so that it's like a doubt clearing lecture. Okay, so please ask your doubts, okay, by Monday. Yeah. Don't delay after Monday, because after Monday, it becomes very busy for me. So if you can give all your doubts by Monday, then I can basically prepare something by Wednesday or Thursday, and I can ask the NPTEL team to post the solutions. Means the lecture with the solutions where I give clarifications.
Sir, thank you again, sir. I would like to leave the meeting.
Yeah. Okay. Thank you.
Yeah, thank you. I'll give you an email, sir. Please look into it.
Absolutely. I'll definitely look at that.
It's been a pleasure meeting you.
Okay. Thank you. But actually several people told that they will join. I don't even know whether they are aware of the time. I think it is posted, no? So I don't know why they did not join. Maybe they have some other class or something. Because others, even Vivek, yesterday only I made some of them. They are again for PhD course or something. They are doing on my course for their PhD or something. But I don't see them anyway. So.
I think
So
we have
then
10
how?
more minutes, sir. I think we have 10 more minutes, right? It's still 11 o'clock.
Oh, okay. So then maybe they'll join. So, Mr. Kaushik, if you have any other question, please ask me, because I think you are the only person here.
Okay, sir. Sir, actually, initially when I was doing some assignments, there was some issue with the understanding of questions. Like in one of the questions, it was given that heat got rejected from the system. When we tell that heat is rejected from the system, my sign will remain same or it gets changed, because my question language is rejected. So it is minus sign or the sign is already considered in the question.
Okay, so actually it is there in the question, because if you follow the lecture, you will see that the convention that we generally follow is heat input to the system is positive.
Yes, sir.
Okay, heat rejected will be negative.
But when we are putting the term rejected itself in the question, rejected means it's giving out. Now I am putting negative.
Yes.
So it will become rejected negative means it will be coming inside. If I
can you give a specific example?
Sir, in the initial, this was in the initial.
No, but you have to give me the question. I don't remember.
I'll not be able to recollect it right now, but this doubt I was having initially also.
So I'll tell you the convention that I follow. So if you look at my board,
yes, sir, this note is I've seen that I've gone through your lecture notes, everything. But the only thing is, one is heat exchange between system and surrounding.
Yes.
And one is heat rejected from system to surrounding. And I'm already putting my word that is already rejected. It's going out from the surrounding. Going out to the
so that means it is that Q will be delta Q will be negative, no? If it is equal to negative, if heat is given out by the system, right?
That is part of exchange, but I am already putting in my question that it is rejected. So already rejecting a part I am including in my question. I am saying that it is already rejected. Once I put rejected negative, there was understanding difference. Otherwise, we know that it is going out means it's negative.
Going out means negative. Yeah.
Yes, sir.
Okay,
but
maybe
when I'm putting
you are telling is that you are confused with the term reject. Okay.
Yes,
okay.
sir. Yes. That was the only thing that once I'm giving in my question that it is rejecting my. So if I put rejected as negative, it is there's only difference of understanding.
Okay, so please give the specific example. We will be careful to use this terminology. So I will use. So basically, it is like heat is given out by the system.
Yes, sir.
Exactly. So it should be
If
like
the
a
heat-
given out instead of rejected. I understand why the confusion is now. Okay, that thank you for pointing this. Yeah, I do understand, because if it is rejected, then it is already negative. So basically, what you are talking about is if it is heat exchange, the
Yes, sir.
heat input is positive and heat output is negative. That's
Yes.
all, or heat given out. Okay, so this might be a terminology problem that is there in the question. Please send me the question so that I can also raise this issue, and we can basically see. There is only one thing that I can do now is basically I can ask the NPTEL team to reject to completely remove that question from consideration when marking the assignment. So you have to give it today itself. There is no time. Okay, 13th is today, is it?
Today
No.
would be, sir.
Yeah, today only. So today is the last day. You
No
send me.
issues, absolutely no issues. It's like learning, not marks.
I understand. Thanks for saying so. But yeah, but anyway, if you require, but it's a very good thing, and it is a really nice, and thanks for the pointer. So we will be most likely more careful while wording the question, because I now understand your confusion. Now, previously I was not understanding what's happening. So what you are basically telling is, if we are looking at heat input or you heat given out, then it becomes makes more sense. But if it's already rejected, then what should I do? Yeah,
Yes, sir.
because that leads to a confusion that it has to be negative.
Yes. Sir, then as you are answering to some other person, Ravikant, that you will be taking some class or you will posting some lecture notes on this use of software, that will be very
Yes.
helpful, sir.
Yeah, absolutely. I'll do that. Myself and my TA, we will sit
Yes, sir.
and we will make this thing. Okay, because I require. See, the problem that happens is basically when I'm recording, if nobody is there. See, thermocal type of tutorial is somewhere somebody has to be there. Okay, so that we can together solve problems. Okay, so but I am going to post that tutorial. Yes, definitely.
Sir, can we attend your classes in person?
This I have to talk to NPTEL team. Okay, so
Like I am in Hyderabad only, so
yes, there is a
I'm a
yes,
student
that
of
is possible.
IITH also. So that way,
Yes, in IITH, I am organizing also a thermocal tutorial session. Okay, at the end, at the beginning of November or in the middle of November, means after Dasera. Okay, so I can share with you guys the online link. However, those who cannot attend also, I have to think of that. So what I am telling is the basic tutorial of thermocalc I will post to all of you. Okay, so where Vivek and myself, we will just prepare the tutorial, and okay, so that the basic ideas are there. But obviously, you can attend the live session. Okay, so because you just drop me an email, I'll send you the link when this tutorial will be given. Okay, from IITH. Yeah.
thank you, sir. So nice,
Yeah.
nice of you, sir. Thank you.
Okay, sure.
Bye.
Sure. Absolutely. So I don't know what's happening. Others are not. So Vivek, I think I don't know what has happened, because yesterday also this NFC people and all that, I think they were they wanted to attend or something. I don't know what has happened.
So I think maybe since people are not there, can we
Uh-huh.
check with these people so that we can close the session? If there are any more doubts, they can post it in the forum.
Yeah. So can we ask them to unmute? Mr. Akshay, can you unmute? I think we can close the phone now, because not only 2 people attended.
I think
Can
we
we
may have to
ask?
call them. I think we may have to call this video people.
You have the number?
I have Prashanti's number. I can call her. Other people, I don't have.
No, anyway, the session ends at 11, no?
Sorry, we told that from 10 a.m. to 11 a.m. is what we want. So
Yes, sir. Yes, sir.
So I think, see, after 2 people, now if anybody joins, it will be very difficult. So
Okay,
can we then close the session?
Okay, sir.
Because,
Done.
only
Thank you,
thing
sir.
is it is not recorded, but
Okay.
there were some people who previously contacted me that they would like to listen to the or have some clarifications. So, but it is not recorded, it seems.
Sir, recorded, sir. This live is recorded, sir.
Oh, this session is recorded.
It's
So
recorded,
can you just put it in can you share this video also?
Okay, sir. I will share.
Okay, so this is basically
Okay.
the live interaction thing. Although only 2 students ask questions, it would be
Okay,
nice
sir.
that other students also know about the doubts and at least possible answers and stuff.
Okay,
Okay,
sir. I
so
will share.
yeah, because otherwise it becomes like if they think that they will join after some time. Okay,
Okay,
10 to 11 it is already posted.
Yes, correct.
They should not feel left out. So as a
Okay.
result, what we can do is we stop this thing, but this
Okay, sir.
recording you share in the class. Yeah.
Okay, sir. I will share soon, sir. Okay, sir.
Yeah.
Thank you, sir.
Okay. Yeah.
Okay.
Thank you, sir. Thanks. Yeah. So shall we close? Shall we leave now?